from Andrew, Devin, Nick, Ben, and me. So before I talk about JProfiling, in detail, let's take a background of auto profiling. So traditional program optimization, statically done optimizations without knowledge of any program execution behavior, forces optimizer to become more conservative. Most often, optimizer bases its decision on program syntax and semantics, which results in a very suboptimal program body that is not optimized for commonly executed cases, as they were unknown during compilation time. Profile-guided optimization or profile-directed feedback is a compiler optimization technique that uses a runtime information collected from a running application to improve performance. This profile infrastructure can provide some of the vital information. For an example, when a compiler encounters particular virtual call or interface call, it needs to resolve that class to call the correct implementation of a method. If known during compilation time that most significant number of time that call would result to a particular class, optimizer can inline that call to make the case faster, which affects on a performance significantly. In statically compiled language, this information is achieved through a training run, which might not reflect a true running behavior of an application. On the other hand, dynamically compiled language can benefit the most out of this infrastructure, as they can compile the method while the program is running. They can have the most accurate profiling information using which optimizers can generate code of a better quality, provided that the past behavior reliably predicts the future behavior. Before I jump into the OpenJ9 profiling story, let's take a look at the classes of information that any runtime profiling infrastructure tends to collect: a code frequency or code execution frequency, which aims to describe how frequently different paths of an application were executed relative to another. This helps us in block ordering and also provides us information about the hotspot in an application where we can put more optimization effort. Value profiling information, on the other hand, aims to describe different values at specific program point, which can help us to generate a code tailored for most frequently executed cases. So how does OpenJ9 collect and utilizes the profiling data? Well, OpenJ9 execution works in a mixed mode where application starts with interpreter methods and frequently executed methods are compiled to native code. So initial profiling information is achieved from a bytecode interpreter loop where interpreter is provided with per application thread profiling data buffer, which it uses to collect raw data from an application. Once this data buffer gets full, IProfiler or interpreter profiler consumes that raw data and passes into a global data structure that can be consumed by JIT compiler. Data collection in an interpreter is very costly operation, so IProfiler also controls data collection by turning it on or off as per requirements. Once IProfiler passes the data into a global data structure, a JIT compiler uses that data in its compilation and also sends out a query to IProfiler to request specific data. So using this infrastructure, we collect targets of virtual call that helps inliner to decide which method implementation to inline, branch direction or switch statements helps us with the block ordering, instance of a check cast runtime types that helps us generating better type case when we are compiling that method. Although most of the JIT compilation are driven through data collected from IProfiler, there are some challenges associated with the IProfiler. First of all, the data collection is really costly, so we only profile last and method invocation. So we only profile last and method invocation when n is tuned as per application characteristic. Most entries in the data buffer is consumed by branch entries. So to reduce time spent on processing those buffers, we skip those branch entries in a sampling fashion and collect a branch bias information just before we are about to compile a method. It requires a separate thread pool to process the data so that we can avoid having pauses in the application thread. And one of the main challenge with the IProfiler is the collection of record that is shut off once the method is compiled to native code. But OpenGA9 can also add an instrumentation in compiled code that is called JProfiler. It can make an exception for very frequently executed methods. Usually a method that consumes significant amount of application running time can be chosen by JIT compiler to undergo special compilation phase that is called profiling compilation. In this profiling compilation, for a given method, we generate two method bodies, one without instrumentation code and one with instrumentation code. Code execution is interlude between these two method bodies based on sampling profiling frequency. OpenGA9 uses a compiler control counter-based sampling in which at various points in a method body without instrumentation code, we have this code that decrements the counter, and upon reaching a counter to 0, it runs an instrumentation code. After returning from instrumentation code, it resets the event counter based on the size of an instrumentation code that it is running. After certain transitions between these two method bodies, recompilation is requested so that a compiler can use the data that is generated by the instrumentation code to optimize the method body. Detailed information about this implementation can be found in Arnold and Ryder's paper, a framework for reducing cost of instrumented code. Although it is really useful to have instrumentation code in a compiled body, there are some challenges associated with JProfiler, which makes it viable option for only a handful of methods. First of all, in the method body with instrumentation code, to get the code frequency, we put the counters on all the blocks on all the blocks. So to reduce complexity during optimizations, we need to limit the certain important optimizations, especially optimizations that, especially loop optimizations. And because of the duplicate method body, the code cache consumption is pretty high. And because of these reasons, JProfiler is only recommended to capture peak profiles, because in this kind of workload, you can collect the required profiling data quickly and trigger the recompilation. So the effect on the runtime would be minimal. So we have seen a software-based profiling techniques. There are some profiling mechanisms which use hardware-provided buffer for profiling data. In OpenGA9, we use those hardware-provided buffer in a sampling mechanism where we compile everything at code optimization level with, of course, lower invocation count to improve startup of a workload. And based on processing those hardware buffers, we try to identify hotspots and compile those methods at higher optimization level. In general, there are so many challenges associated with the use of hardware buffers in profiling, but the main challenge is limited information in virtualized environment that makes it unusable in cloud environment. Its implementation is hardware dependent. The hardware sampler we have in OpenGA9 has two different implementations, one for Power and one for Z platform. Collecting value profiling information and a block frequency information becomes very costly and complicated with this kind of infrastructure. So that's why we kept its usage limited to sampler only in OpenGA9. So we have seen software-based profiling techniques used in OpenGA9. We have seen hardware samplers used in OpenGA9. Why do we need multiple profilers in first place? To answer that, we need to see two main categories of workloads under which JVM falls in. A workload with hotspot. Significant amount of application running time is spent in handful of hot methods in this type of workloads. This handful of hot methods will be compiled to native code and might inline some other methods as well. So to get a real current context about an application, data collected from IProfiler from early on run might lack the information about inline methods. So JProfiler comes here because it can add instrumentation in compiled code, and it provides us the current information that we need to compile these methods, recompile this method to help us improving throughput. Flat workloads. Running time distribution is pretty flat in this type of workloads. To improve performance in this type of workload, we need to compile as many methods as quickly as possible. And startup time is really important in this type of a workload. Because of the higher code cache consumption and dependency on a recompilation, JProfiler becomes really impractical to use with this kind of workload. And IProfiler provides here necessary information that we can use to optimize those method bodies. So we have seen challenges that we faced with different profilers. What do we expect from a standard, from an ideal profiling infrastructure? Well, we want to have a single framework for both startup and throughput improvements. We want to have a profiling code for a large number of compile methods with the minimal impact of minimal impact on a compile time. So cost of adding instrumentation code in the compile body should be minimum. We also the compile body with added instrumentation in it should not have any impact on a throughput if data collection is turned off. So in case if we don't see any benefit from a recompilation, we can just turn off the data collection and continue running the application without any throughput impact. So, and also the data collection and the processing should be efficient so that we can collect the required data with minimal usage of resources. So with these goals in mind, JProfiling implements two different mechanisms, one to collect a code frequency and one to collect a value profiling frequency. Let's talk about how JProfiling collects code frequency. Well, one of the main problems JProfiler had was it in the method body with instrumentation code. It has a counters on all the blocks to get the code frequency. JProfiler tries to aim to minimize this counter. How can it does it? How can it does it? Let's take a example intuitive. Let's take a look at an intuitive example. So in this example, we can decide to naively put counters on all edges. But is there some better way we can optimize this? Well, we know that if we put a counter on a blocks with a single successor or a single predecessor, we can effectively counter frequency of other edges and blocks. So that reduces the counters to half. Can we still do something better? Well, for some, if somehow we know the method entry frequency or the exit frequency, we can leave out the counter from the frequently executed path and have a minimal effect of adding counters on running time. So with this intuition in mind, JProfiling employs a counter placement algorithm based on this two papers. One is written by North and Stevenson's that describes CFG reduction procedure to optimally profiling, and another is Bell and written by Bell and Ross that provides us comparison of different algorithms about tracing programs. And based on these two papers, we prepared a formulation based on CFG edge execution frequency profiling. Let's take a look at the example how JProfiling minimize the number of counters we need. This is a simple control flow graph with one back edge. It can represent a for loop or while loop in any method. Let's see how we can minimize the number of counters in here. So first of all, what JProfiling does is to implement a maximum spanning tree out of that control flow graph. And just to get the maximum spanning tree, it adds an artificial edge between start block and exit block to emphasize that the number of times you enter into a method is equal to number of times you exit into a method. So after it, and it also uses the Prim's algorithm to obtain the spanning tree. So once it obtains a spanning tree, I have just highlighted those edges which are not present in the spanning tree with green color here. It traverses through all the edges and tries to find out the edges that are not present in the maximum spanning tree and put counters to measure those edges. So in this case, we just need to count edge 4 to 5 and 5 to 1. So we put a counter to measure edge 4 to 5 and edge 5 to 1. Once it has put the required counters on all the paths, it prepares a formulation in terms of addition and subtraction of that counted blocks to get the frequency of uncounted edges. A detailed implementation of this algorithms can be found in JProfiling block.cpp of J9, and let's see how we can obtain a frequency of uncounted blocks. So let's take an example. We want to get the frequency of block 2 that is not counted. Well, we know that the block 2 has a single predecessor. So if we get the frequency of edge 0 to 2, we can get the frequency of block 2. We can see that the edge 0 to 2 is a single successor of block 0. So to get a frequency of edge 0 to 2, we just need to get the frequency of block 0. Block 0, which is a start block, that means the frequency of block 0 is equal to frequency of block 1 because number of times you enter the method is equal to number of times you exit the method. So it becomes intuitive that to get a frequency of block 2, we can just get a counter from block 7 and obtain the frequency for block 2. So following these steps, it can prepare a table to find out frequency of uncounted blocks or edges to get the in terms of block numbers that contains the counter that we need to load or add or subtract together. In this example, there are no requirement to add or subtract any counters together, but we can assume that in a complicated control flow graph, we would have some blocks that we need to add or subtract together. So we have minimized the number of counters that we want to put in a control flow graph. We have prepared a formula that requires to obtain a frequency for uncounted paths. How do we store this information? Well, it uses a persistent ture block frequency information info data structure to store this information. This data structure contains array of pointers to a bit vector that holds an information about which counted blocks it needs to add or subtract together to obtain a frequency of counted blocks. So in this array, if we have a null entry, that means there is no counter available. If that entry is low tag, that means we can efficiently obtain a frequency from single counter. And with single mathematical operations on that entry, we can find which block counter from which block number we need to load to get the frequency. If the entry is not null or not low tag, that means it contains a pointer to TR bit vector, which holds an information about which counters it needs to add or subtract together to get the frequency. Detailed information about this data structure can be found in j9profiler.hpp or CPP file. So the benefit of this algorithm is in a cyclic region. It has at most one counter, and implementation favors counters at lower frequency edges and blocks. So it reduces the tag contentions while we are updating the counter. It can compute the frequency of any single block as a sequence of addition or subtraction operation, and the block frequencies are stored using pair of bit vectors. That means it provides a high information density. So in my example, one of the main part of our OpenJ9 was exception, which I did not show. How does JProfiling handles exception with this algorithm? Well, exceptions are special in OpenJ9 as they can represent a non-local control flow, changes in a non-local control flow. And if we decide to put a counter on all the exception edges, we need this many counters to get the frequency of all the blocks in the program. But we have simple observation that we made about exception edges, that they are rare and usually do not occur. So using that observation, we can simplify an assumption and combine all the counters from exception edges and put them onto the catch block. As currently in OpenJ9, we know how to exploit the information on a catch block, and we do it, but we don't have any mechanism that exploits information about counters on exception edges. So we can take that assumptions and put counter on the catch block. So how does JProfiling handles inlining? Well, inlining is special because it can change compilation to compilation. So if we are compiling a method and found out that the method is not inlined in the previous profile body, then it goes into a sim call chain and tries to find out information about that method. If it does not find any information, then it uses a IProfiler data about that method. In this algorithm, counter are placed very early in a compilation phase with associated bytecode info that reflects ILGen state. And optimization can co-locate or deduplicate the counters. As we already have minimized the number of counters that we are putting in a control flow graph, we are not limited when we want to apply certain optimizations, which we were in case of JProfiler. So we have seen how efficiently JProfiler optimizes the number of counters that it requires to put. Let's take a look at how it employs a value profile, how it collects a value profiling information. Well, main aim behind value profiling information is to identify common values and program properties at specific points during program execution. This information can be type of object, that which is a type test like a check-cast instance of virtual method dispatch. It can be a loop induction variable or length of arrays. And using this information, an optimizer can generate a code tailored to frequently executed cases. So the main lookout in any value profiling information is to detect a consistency. So from given value profiling information, only small set of information is of interest, so that compiler can use that information to generate better code. Lack of this consistency suggests that there is no commonly executed cases present in the method body that optimizer can exploit. So using this idea, JProfiler only profiles most frequent n values, where n is a small integer, with keeping track of uncounted cases. That also provides us information about the inconsistency. So how does JProfiling data stores the value? Well, it uses a hash function to store the value. That hash function contains two arrays, one with the value information, one that contains value that provides us information about which values we are profiling, and the other one contains the frequency of corresponding value. It uses a bit extract as a hash function that extracts the bits out of a value and gathers it in a zeroed integer to effectively generate an index into array. So to update or add a new value to a table, first of all it generates an index to an array using the hash function, and it checks in the array if that value exists or not. If that value exists, then it just increments the corresponding counter and continue running the main code. If that value does not exist, then it tries to check if the table is full or not. That means if it can add new values to a table or not. If it cannot add new values to a table, then it contributes that value to uncounted cases and continues running main program. If it can add new values to a table, it attempts to lock the table and checks if the table is locked or not. If table cannot be locked, then it again contributes that value to uncounted cases and continues the execution of a main program. If it can add a new value to a table, then it rehashes the table to make sure that most frequently profiled values are not kicked out in case of collision, and add new value to the table with initial counter, unlocks the table, and comes back running main program. So with this infrastructure, it gathers the precise frequency information for only small set of values while keeping a counter for other uncounted cases as well. And as I have shown you, incrementing a counter is very cheap. That can be done inline without going to any complicated C code. If uncounted cases becomes more significant, then it is really easy to clear out the whole information and start populating the table from scratch. And the efficient hashing mechanism that contains a bit extract are probably optimized on all platforms with single instruction. This is a simplified version of how trees look like in our IL. I just simplified the trees. It uses an itinerary to decide if it wants to increase the other counter or the frequency counter, and just check if the table is full or not here. And depending on what, it either executes the increment part or calls the helper to add new value. So current status of JProfiling in OpenJ9. Right now we are enabling JProfiling for profiling compilation, effectively trying to replace a JProfiler right now. And while doing that, we had some of the challenges that we tried to address, like it was very slow in triggering recompilation in methods with loop. Initially, it was just using a method invocation count to trigger recompilation of a method. So if you have a method that spends so much time in a loop, you'll stuck executing profiling method before tripping recompilation. So we added a recompilation testing loop to identify these cases. Because of a block splitter, the compilation time was increased in global register allocated. So we reduced the number of blocks that we had for adding a profiling value. It was profiling multiple value in same value multiple time in extended basic blocks. So we removed duplicates as well, and it requires tuning because we wanted to decide how much data is enough for us to get the proper optimized body. Performance results, I have just put out the numbers of iLog. On x86 and on power, iLog 300 toolset improved by 5% when we switched from JProfiler to JProfiler, while on Z it improved by 2.3 to 2.5%. Future work, we want to enable this infrastructure for warm bodies, and we basically want to have this profiling instrumentation code for large number of bodies. There are some challenges that we have faced with while we were enabling this for the profiling compilation, as increased compilation time in global register allocated that we are trying to address right now. And we need to have a mechanism that allows us to do a reverse patching, because currently in OpenJ9, we can only patch a branch to a node. It's not possible to do vice versa. Questions? In the JProfiler? So in the profiling compilations, effectively you don't want to disable the counters.
The question is, are you creating a profile compilation, body profile, like your information that goes away?
Yes, right now it does it. We are working on enabling this infrastructure for warm bodies, where we are going to apply some mechanism in which we can have a single body that can yeah.
I thought that was the original.
No. For the profiling compilations, because it is anyway going to get away when we compile it at a scorching level, we don't care about patching or reverse patching.